Hi, everybody. Chapter 24 of Young and Friedman, or uh, whichever chapter it is in the text that you're referring to, that discusses capacitance and dielectrics, is the next topic that we're considering. And I expect this particular recording to be relatively short. There isn't too much um, new equipment we have to define. Most of this we already know, and we're chasing down a couple of the consequences of the first few chapters, 21, 22, 23. We defined electric field, we've defined the relationship between charge and field, and we've defined electric potential as a way to sort of interrelate and make some calculations a little bit easier. Now that we have electric potential and electric field and we can push charges, we start to wonder whether we can get those charges to do something for us. And we start that work here in this chapter. So, what are we talking about? In this chapter, we will talk about capacitors, the energy stored in a capacitor, what dielectrics are and how they work, and what their presence can do to change Gauss's law. It's short, it's 5 bullets. Capacitors have applications in flash photography. The energy used to make the flash very bright, very short amount of light is stored in a capacitor, two closely spaced conductive elements that carry opposite charges. The energy that is used to illuminate the flash is stored in the electric field set up between those two conductors. Okay, let's see what's going on. Any two conductors separated by some non-conductive thing like a vacuum or an insulator is technically a capacitor. If we're talking about a charged capacitor, then these two conductors in our convention, when we say the capacitor is fully charged, what we mean is that the one has a magnitude charge and the other has the same magnitude of the opposite sign, so that the net charge on the capacitor together is 0. All right. The sort of quintessential go-to example of a capacitor is that of parallel plates. And we've talked a little bit about parallel plates before, so we can say some of what we need to say off the bat. So we know the electric field above the positive plate is 0. Sorry. Hold on. Let me do it this way. And the field below the negative plate is also 0. We saw that when we looked at the parallel plate configurations in the simulator that was the link that I shared. As the plates get large compared to their separation, between the plates, the field is almost uniform, and outside the plates, the field is almost 0. In between the plates, we know that the field is related to the surface charge density magnitude on each plate. So we know that the electric field between the plates, which we know points from positive to negative and is uniform throughout the region, except for like right at the edge, there's some fringing effects that curve the field a little bit, but let's ignore those. As long as these are big plates and they're close together, almost the whole field is uniform down in this picture. That the magnitude of that field is related to the charge density and the permittivity. Now, the charge density has to do with how much charge there is and how much area we're spreading that over. Okay, fine. But back in the previous chapter, we said that the potential difference between one plate and the other plate, let's say that that's A and this is B, that the potential difference of point A relative to point B is the negative of the line integral E dot dl. Now, the electric field is in the down direction, and dl from B to A is in the up direction, so the dot product is negative. But the directions, they're anti-parallel, so we just get a minus sign. It's the field E, which is uniform. We can pull it outside the integral, and we're just integrating dl on the distance d between the two plates. So we're going to end up with negative ed, and the answer is just ed. So we can say that the potential difference between the two plates, VAB, is the electric field times the separation distance. All right, so let's put that all together. The electric field magnitude, and we're only talking about the magnitude now because that was a dot product, it's all scalar. The potential difference VAB between the plates, let's replace the electric field magnitude with what we know it's equal to. At a certain point, we just use the symbol V to talk about the potential difference because we have the subscript, the potential difference between 2 points A and B. Field magnitude charge over area epsilon times D. Now, how good is this capacitor, this thing, at storing charge? How much potential difference do we need to set up between these two plates in order to store a charge magnitude Q on each one this far apart? Because as we build charge, the field increases, and it takes work to move charge. As we start to put more and more and more charge, it's going to be harder and harder and harder to keep them where they are because they're attracted to each other. So, how much charge can we store for a given potential difference? So I'm looking for charge per potential difference. If I'm able to set up a potential difference, V sub AB, how much charge can I store, positive and negative, on these plates? And if we rearrange A epsilon over D, and that's how good this arrangement is at storing charge for a given potential difference between the plates. Let's define that as capacitance. Like capacity, how much charge for a given size bucket. If we have delta V, if we have a potential difference to play with, how much charge can we store? Capacitance. Cool. And in fact, we've already written the capacitance of a parallel plate arrangement is the area of the plates times the permittivity divided by the plate separation. And there it is. The cool thing about capacitance is that it depends only on the geometry of the plates themselves, and I guess what's in the space between them. What is the permittivity of this space? What's the area? And what is the separation? Cool. Parallel plate capacitors are actually used. It's not just an idealization. We use them in microphones. One plate is fixed, the other plate can move. And as sound is incident on the microphone, that other plate gets pushed by the sound. As it's pushed, it changes the separation, which changes the capacitance, which changes the relationship between charge and voltage, potential difference, which induces charge to flow one way or the other. That flow one way or the other can be converted and amplified and recorded. The unit of capacitance. Wait, hold on. We know what it is. It's coulombs per volt. Or if we chase down the units of, so this is area, so that's meters squared divided by distance. So that's meters squared over meters. Okay, so it's just meters, but we got to remember what the units for the permittivity are, and I'll save us the time. We end up with Coulomb squared per Newton meters, but Newton meters are joules. So we have a handful of different ways to talk about capacitance, and the last one is the defined unit named after Michael Faraday, the farad, or farad. We'll use the symbol F, the unit of capacitance. Most capacitances are on the order somewhere between nano to millifarads. As it says, 1 farad is substantial. That's a large amount of storage. Microfarads is very common, and in fact, we see a picture of some 1,000 microfarads. So I guess that's 1,000 micro is 1 millifarad. What if we have more than one of these arrangements? All right. So you might already see that we're starting to point towards circuits. I mean, I talked about charge flow a second ago. We're eventually talking about current. But before we do, we have this new animal, this capacitor. How does it behave? The potential difference between points A and B is as a result of what's between them. In order to get from B to A, as drawn, we have to go through C to get to A. So from continuity, right, the potential difference of C relative to B plus the potential difference of A relative to C gets us the total potential difference of A relative to B. All right, fine. But the potential difference from A relative to C means that we're on either side of this first capacitor. And if we have our relationship C equals Q over V, then we can solve for the voltage Q over C. So V1 is Q1, I guess we'll say Q, because it's labeled Q, Q over C1. V2, by the same logic, is that charge Q divided by that capacitance, C2. And we're supposed to add these things according to this rule. So the potential AB, potential difference, is sum Q over C1 plus Q over C2. How much charge did we end up moving? Well, we've got charge Q here, charge negative Q here, and that is going to function to induce these charges on the opposite plates. We attract positive charge towards this negative one, and we attract negative charge towards that positive one. We only ended up storing Q once on the outer plates. We've got stuff between them, sure, and there's induced charge there, but we only stored opposite magnitudes Q on the outer plates, at least as far as points A and B are concerned. So the potential difference AB is what it looks like if we store a charge Q with an equivalent capacitor such that these two sides are equal. And we end up with this relationship if we divide through by Q, that the equivalent capacitance of two equal capacitors in series, I guess they don't have to be equal, we're calling them C1 and C2, is the reciprocal of the sum of the reciprocals. It's not particularly pleasant to work with, but it is what it is. If there were more, again, we need the reciprocal sum of the reciprocals. So that's sort of in sequence, one capacitor, then another one, and what does the arrangement look like? What if we put them next to each other? Now, the potential difference across capacitor C1 is the same as the potential difference between A and B, because these wires, these connections, are idealizations. There's no potential difference from this point to this point. It's basically both point A. So asking for the potential difference across C1, V1 is Q1 over C1. But V1 is the same as V, which means it's also equal to Q2 over C2. So, because again, this is point A just as much as this point is, just as much as this point is. So how much total charge are we storing? Imagine that this is just one large plate over top of one large plate. We can store more charge if we align them so that they're experiencing the same potential difference. It makes sense that the capacitance would increase. The total charge Q C1V plus C2V. And if we imagine an equivalent capacitor, the charge Q on that would be according to its equivalent and the same voltage. Because again, we're going to replace this whole arrangement with one equivalent such that the voltage is V and the total charge is the charge that we're storing, Q1 and Q2. All right, so we can cancel the voltage that is the same on all the terms of this equation, and we end up with this. If there were more than two, we'd end up with this. Cool. Energy stored in a capacitor. Here are some relationships. Now, where did they come from? For this, we need to do a little bit of writing. Last unit, last chapter, last lecture, we said that the work done to move a charge Q through a potential difference is that. So if we talk about a very small potential difference, well, let's talk about a very small amount of charge. Through some potential difference, V. Oops. V. We could integrate this. But the potential difference from one side to the other of the capacitor arrangement depends on the charge. C is Q over V, so V is Q over C. Okay, dq, Q over C. So we integrate the work. We integrate the right-hand side. The capacitance is a constant depending on the geometry of the arrangement, so we can pull that outside. And we're integrating Q dq, so we end up with Q squared over the capacitance. How much work do we do to store charge Q on a capacitor of capacitance C? That much. But we could use these relationships to rewrite that. The charge Q, for example, is the capacitance times the voltage. So this is 1/2 CV squared over C, and we end up with 1/2 CV squared. Okay, the capacitance itself is Q over V. So it's 1/2 Q over V, V squared, and we can cancel the V and end up with 1/2 Q V. Are those the three relationships that we just looked at? Yeah, I think so. In order to move the charge, we have to do some work because as we set up a potential difference, it becomes harder to store more charge. The charge that's there on the positive plate wants to repel the additional positive charge we're going to put there. So we end up doing additional work every charge we want to add. If we're doing work against a conservative force, that work is stored in the configuration as potential energy. So, how much potential energy is stored in the electric field that's set up by a capacitor? Exactly as much as the work we do. Suppose we're interested not just in how much energy, but how good our geometry is at storing energy. So we talk about not the potential energy, but the potential energy per unit volume. In other words, because our capacitor is taking up some space, these plates they have an area and a separation. That's a volume. So they're taking up some space. So how big a volume do we need to store this much energy? Well, let's call it lowercase u is equal to capital U divided by volume. And I'll write VOL instead of V because we already have voltages, and I guess I should write volume because the potential energy, let's try 1/2 capital C capital V squared. The volume is the area of the plates times the separation. But the capacitance itself is related to the area of the plates and the separation. Okay, so the area cancels, but the d becomes d squared. Epsilon v over d squared. And if we look back a few slides, several slides, the potential difference is related to the electric field. If we divide both sides by d, we get the electric field magnitude. So whoops, that's where we were, sorry. So we could replace V over D with the electric field magnitude, and yeah, we end up with that expression. There's no need for me to write it again. It's right there. How much energy can we store in a capacitor or a capacitor arrangement? A large number of capacitors in parallel, which means a huge equivalent capacitance because we keep adding the capacitances of them to talk about the equivalent. The arcs that are shown are produced when these capacitors are discharged at their target, when we can heat it to 2 times 10 to the 9th. Okay, so 10 to the 3 would be 1,000. 10 to the 6 would be million. 10 to the 9 is 2 trillion Kelvin. As a result, of the energy that we've stored in this capacitance arrangement. Now, geometry isn't the only way we can affect the capacitance because, remember, the capacitance has to do not only with the plate area and separation, but the permittivity. Suppose we put a different substance between these two plates other than vacuum. If we're using vacuum, that's fine. If we use a dielectric, we didn't change anything about the charge that's stored. We're just measuring the potential difference across the two plates from one to the other. Inserting the material decreases the voltage experimentally. For the same Q, hold on, for the same Q, we decrease the voltage. Decreasing the denominator increases the fraction. So by inserting this material, we have increased the capacitance. What is going on? What's actually happening? If the voltage is decreasing, the electric field must be decreasing as well. And what's happening is that we're inducing surface charge on the inner surfaces of this material that opposes, is attracted to the charge density on the plates of the capacitor itself. Now, the dielectric is an insulator. So it's not that there's, it's not that we get flow and then charge cancellation, I guess. But we do have a buildup. We have a buildup because we have changed the permittivity. We said back when we were talking about Gauss's law that the permittivity is how many permits we need to fill out in order to erect an electric field. And if it's not vacuum, it gets worse. We need to do more permitting to set up an electric field for a given charge Q. It's more permittive. And we end up changing the permittivity by a factor K, or kappa, which is called the dielectric constant. Here's the original capacitance, and we increase it by a factor K, kappa. So we can think about kappa epsilon as the new epsilon, the permittivity of this material, this medium. How easy, how difficult is it to set up an electric field as a result of having some charge? Epsilon. If we're changing the environment, we have to change the energy considerations as well. And so we see kappa showing up here and the new permittivity. Sample dielectric constants kappa. Vacuum. Air is very close to vacuum. Pure distilled water, it's very high. 80 times the permittivity. It's 80 times harder to establish an electric field in distilled water than it is in vacuum. I guess that makes some sense. I mean, there's a lot going on in water. There's intermolecular bonding and who knows what else going on that's affecting our ability. It's a liquid too, so I mean, things are moving around. It's hard to get anything permanent set up, and this is an expression of that. Dielectric strength. Don't confuse dielectric strength with dielectric constant. The dielectric strength has to do with the maximum electric field that the medium can withstand before its insulative properties break down. The insulator becomes a conductor if we apply too large an electric field or too large a voltage over a particular distance. And we've talked about that shock that happens when you touch the doorknob. It's because we've locally broken the dielectric barrier for air. We've ionized the molecules, and now the air conducts, and we get the spark that zaps your finger. What's going on, really? Some molecules, like water, are naturally polar. In an electric field, they tend to orient themselves. And you see that the negative sides are collecting on the left side of things, and the positive sides are collecting on the right, as opposed to here where they're all random. Even if it's a non-polar molecule, we can still induce some local preferential dielectric field to the right, pushes the positive to the right and leaves the negative, pulls the negative to the left, and we end up with induced dipolar character, and then the dipoles try to align. So whether they're polar or not, we're still going to get some alignment, and this is related to the same idea that a neutral object is attracted to a charged one because we're inducing some charge. So whether the molecules are polar or not, we're inducing some alignment, and we'll call this polarization. We've made the molecules polar and we've aligned them this way. Now, note the electric field, the dipole moment of a dipole points from the electric field points the other way. So that induced polarization field acts against the electric field that's set up between the charged plates, which explains why the electric field magnitude decreases, even though the charge magnitude, charge density on the plates themselves hasn't changed. The induced charge can get in the way. Now, this is potentially problematic. If we start thinking about Gauss's law and we draw a Gaussian box, third dimension not shown, we have to include this charge. And the answer is no. We include the free charge, not the induced polarization charge as a result of reorganizing the molecules in the dielectric. We still only care about the surface charge density of the conductor. But we do need, if we're evaluating the flux through this surface, we do need to keep track of the dielectric constant. And the electric field is reduced because the dielectric constant accounts for the fact, these are not free charges. This positive charge is, you can think of it as bound with this negative charge. They're bound together. They're attracted to each other and they're kind of stuck. This one is free and free to set up an electric field. Why is Q less? Well, because the dielectric is binding. How much less? It's related to the dielectric character. Total free charge divided by epsilon. Now, I'm thinking about dividing both sides of this equation by kappa. Because it's a constant. Oops, not zero. This is the original expression. The electric field is going to be less because we're dividing by a greater permittivity. Total free charge. You know, I think we got to go back. The free charge, that's these guys. This negative charge right here is a representation of this. This is not a conductor. These charges are not free to move around. We're setting up alignment between molecules, but we're not taking this molecule and moving it around. The free charge, which is the charge we had before, divided by the additional permittivity associated with this interaction. Check out this link for additional information about Gauss's law with respect to dielectrics between conductors. And believe it or not, that's it. We will practice these ideas for sure, the recitation and the activities, but as far as new content, that's what we're talking about. Thanks for your attention. See you next time.